So what we're going to discuss here today is something called the cross product. And the cross product as a calculation is nothing too terrible. If not, it's a little onerous in terms of like it's kind of tedious. And the bigger that we are in terms of the space, going from 2 dimensions to 3 dimensions to 4 dimensions, the harder it is to actually do the cross product. But or not harder it is to do the cross product, just like the more vectors that we kind of need, and it just it's harder to do the bigger that we get in terms of its dimensions, in terms of its calculation. But let's just think about it in terms of 3 dimensions. And what I want to talk about it is geometrically what it means. So what the cross product is this calculation that generates a vector. It's going to create a vector. So the dot product gave us a scalar. So when we took the dot product, we ended up with a scalar. But when we actually do the cross product, we're going to end up with a vector as the result of doing the cross product. And that vector ends up being very special. So in order to find the cross product in 3 dimensions, we're going to need 2 vectors. Okay? We're going to need 2 vectors. And what's going to happen is I'm going to imagine that here's my first vector. Let's say it moves in this direction. All right? Okay? We're not going to really worry about the length at the moment. We're only going to be worrying about the direction of the vector, although we are going to get a length as well, or our magnitude as well. So let's say it moves in this direction. And so I'm going to utilize my right hand. Okay? And this is where we get this idea of the right hand rule. This is where it actually becomes really important. So I move my right hand. Okay? And then what I'm going to do is I'm going to curl my fingers in the direction of my second vector. So let's say the second vector is over in this direction. So there's the second vector. Okay? And the position of my thumb, okay, so the position of my thumb, that's the direction of our cross product. So here's my first vector, my second vector, okay, so I'm going to take my first vector, then I curl my fingers in the direction of my second vector, and then there's the position of my thumb. Let's say, for example, this is my first vector, but my second vector points this way. What I'm going to have to do is I'm going to have to actually turn my hand in order to, in fact, get that direction of the cross product again. So basically, there's first vector. My second vector points this way. So now if I'm going to turn my hand my fingers, okay, or curl my fingers in that direction of my second vector, then my cross product is now pointing downward. And that's what we talk about with the right hand rule. I mean, if you kind of imagine, okay, so now here's my first vector, okay, and see my second one is doing that way, is moving in that direction. So now I've got to turn it this way, and my cross product is now pointing in this direction. Okay. You don't really need to be able to generate something where you're like, oh, it's okay, it's going to be in this direction, etc., etc. The vector that you get is going to tell you the direction. The reason why we do this right-hand rule thing, though, is to actually show that this vector, the cross product vector, is in fact orthogonal to my 2 other vectors. It's orthogonal, and that's actually crucial. That's a crucial fact, okay? That what we've done is, by taking the cross product of these 2 vectors, we found a third vector that is in fact orthogonal to the other 2, right? That is that when you take its dot product, it ends up equaling 0. Okay, the dot product ends up equaling 0 for both vectors, all right? And we form a 90-degree angle, okay, with each one of the vectors. So those 2 vectors, call them x and y, or v1, v2, whatever, uv, u and v, okay, they don't need to be orthogonal. But what happens when you take the cross product is we generate an orthogonal vector as its result, okay? And that's what we're demonstrating when we demonstrate the right-hand rule. Okay, so let's now talk about how do we calculate the cross product. So let's suppose that we have 2 vectors. We've got u, which equals u1, u2, u3. So it's in 3 dimensions. And we've got v, which equals v1, v2, v3. And we're going to construct a vector called u crossed with u crossed with v. Okay, u crossed with v, and notice it's got an x. That's not multiplication, that's actually finding the cross product. Very important. Multiplication is actually just going to be represented by just nothing, right? You put something next to another thing, that's just multiplication, okay? And so, the dot product is going to have a dot, and then this is going to be representing our cross product. So u cross v is going to end up being, it'll be another vector, okay?
the vector, how we might write it, we'll have it as, we're going to take, for our first component, we're only going to be looking at the last two components in u and v. So it's going to be u2 v3 minus u3 v2, comma, and then what we'll look at is we'll look at the first and third. So the ones that are not the one that we're actually finding inside of the cross product. So this is now going to be u1 v3 minus u3 v1. Okay, and that's actually going to be negative. And then we'll have the first two, and then we'll go back to a positive. Okay, and that positive, it's going to be then, it'll be u1 v2 minus u2 v1. And those are the components. What you're going to see this cross product written as more often than not is you're actually going to see it written in the standard unit form. So it's more often than not going to be written as u2 v3 minus u3 v2 I plus, or rather minus u1 v3 minus u3 v1 j plus u1 v2 minus u2 v1, and that's going to be our k. Right? Notice I made a couple of mistakes, like, oh, we got that negative. So the jth component inside of the cross product is going to be a negative. So don't forget that that's the case. Let's do a quick run through. Let's actually do the cross product real quick here. So we'll find the cross product. And this is going to be 4. We'll have u equal, okay, 1, 3, negative 1. And we'll have v equal 2, 2, 0. Okay, we'll have 2, 2, 0. And we're first going to find u cross v. So u cross v is going to equal, so we're going to start out, we're going to utilize u2, u3, and v2, v3. So I'm going to take 3 times 0, okay, so 3 times 0 minus, okay, and then it'll be negative 1 times 2. All right, so the second times the third minus the third times the second. And then that's going to be I plus, now we'll take the first, so the first times the third, because we're looking for the second, so we're actually going to look for the second. The first times the third, so 1 times 0 minus the third times the first, minus negative 1 times 2. Notice I'm not going to have a plus, right? I'm going to have a minus sign there. And that'll be j. Plus, and this will be then 1 times 2. So first times the second, minus the second 3 times the first 2, and that'll be my k. And so this ends up equaling 2i minus 2j plus, and then this is going to be 2 minus 6, so, or minus 4k. And that is the cross product of u cross v. Okay? You might ask yourself, and this is actually really is a pretty good question, of whether or not if I actually switch that, if I did v cross u, are they actually what we call commutative? And the answer is no, they're not. Okay? So v cross u, so now if I rewrite v cross u, take a look at what happens. Okay? So what we're going to start out with now, v is, we're going to have, here's my second and third, and my second and third inside of u, so they're still the same, it's just that we're now going to be doing 2 times negative 1 minus, and then this will be 3 times 0 and that'll be I, and then minus again, because that's our cross product, and now this is going to be negative 1 times 2, okay, because we're going to be looking at, or rather 2 times negative 1, because 2 is now the first value, that's v1, and here is u3 minus, okay, and then it'll be 1 times 0, because this is now going to be v3 times u1, and that'll be my j plus, okay, we'll have 3 times 2, so now that would be 1 v1 times u2, so 3 times 2 minus, and then this would be then 2 times 1. Or actually, it'd be 2 times 3 minus 2 times 1, and that would be k. And so when we compute this, what we get now is we get negative 2i minus, okay, and this would actually be plus 2j, because see how it's 2 times negative 1, so it's plus 2j, and then plus, and that's 6 minus 2, so plus 4k. And that ends up equaling our cross product. That's v cross u. Super important to notice is that u cross v, okay, equals negative of v cross u. They're not actually commutative. They're not going to be the same thing. They're going to end up being negatives each other. And that's going to be actually one of the first characteristics of the cross product that we're going to look at. I'm going to enumerate those in just a second. I'm not going to go through and prove them because it can be really tedious and really just involved. I really recommend you take a look at your book if you want to kind of work through all of the equations and the calculations. So we've got our calculations there. So let's look at, we're going to actually generate an alternative calculation for the cross product. The alternative way of doing the cross product. It's going to become really important. We're going to give it another name. So we have an alternative calculation. And so let's say, for example, I've got u equals, and this is going to be 1, negative 1, 3. And v ends up equaling 2, 4, negative 5. What I'm going to do is I'm actually going to set up, something called a matrix, okay? And so what it's going to have across the top, it'll have I, it'll have j, and it'll have k. And then I'm going to have u, I'm going to put u first, 1, negative 1, 3, and then 2, 4, negative 5. All right? And then it's going to be v. So u is going to go in the first slot and v is going in the second, and that's because we're going to try and find, in this case, u cross v. If it was v cross u, we'll do that in a second. You're actually just going to switch the two, okay? Where v is going to be the second line and u is going to be the first. So what we're going to do with that is we're going to first start out, we're going to say, okay, I've got I, okay, and I is going to be, we're going to take what we call a cross product, literally a cross product, and this is where it comes from. Negative 1 times negative 5 minus 4 times 3. So I've got negative 1 times negative 5 minus 4 times 3, and that'll be I. Okay? And so we multiply that by I. Now I'm going to go to j, and j is going to utilize the first and third columns now. And we're going to take its cross product. So now we're going to take 1 times negative 5 and 3 times 2. So this is now going to be minus, remember that's a minus, minus 1 times negative 5, minus, and now this will be 2 times 3, and that'll be j. And now we're going to use k, so we go to k now, and k we're only going to use the first and second terms. Okay, so this is going to be plus 1 times 4 minus 2 times negative 1. And that's k. Notice how much easier that is. Okay, kind of keeps things a lot simpler for us in terms of keeping all of our values together. So that's negative 1 times 5. So that's negative 5 minus 12. So that's negative 17i minus, and then this is going to be negative 5 minus 6. So that's negative 11. So negative 11 and negative. So it's going to be plus 11j. And then 4 plus 2, right? So plus 6k. And that is the cross product u cross v. Let's do it with v cross u. So now I've got v cross u. I'm going to have I, j, and k. across my top. And then now I've got 2, 4, -5, and 1, -1, 3. And now I'm going to do the same calculation. So this cross product is going to equal now 2 times -1, or excuse me, not that, but 4 times 3 minus -1 times -5. So it's 4 times 3 minus -1 times -5. And that'll be times I, plus, then we'll take the first and the third. And that'll be then 2 times 3 minus 1 times -5. And that'll be j, plus, and then we've got k, and so that's going to be the first and the second. So that's going to be 2 times -1 minus 4 times 1, k. So this ends up equaling 12. That's 12 minus 5, so that's 7i. Or, excuse me, this should have been -7i. Sorry. So this is going to end up being 7i. Okay. And then we have 6 plus 5, so that should be, and then this is a minus, right? Because it's the j. So this is minus 11j. And then -2 minus 4, so at minus 6k. Okay, no, sorry about that. That should have been a -7i. Ended up subtracting 5 instead of adding 5. So notice v cross u and u cross v used in this method, they're also negatives of each other again, right? We're going to have that property. That property is going to be called being anti-commutative. Okay, so it's going to end up being anti-commutative. All right, so now the next thing we got another result that actually is going to be really handy for us. I'm going to go and prove it calculationally in just a little bit, but what I'm going to do first is I'm actually going to talk about it from the perspective of the right-hand rule. So let's say, for example, we've got x, the x-axis, and that's our I. The vector I is the x-axis. So let's say, for example, you kind of want to imagine in 3 dimensions. Well, I is the one that points out towards you, right? From my heart out to you, okay? And then the j-axis, which is my y-axis, that's the one that's kind of like the parallel if I kind of stretched out my arms. So now, like, I want to imagine, okay, here I am, and if I start out with I, and I cross with j, remember, like, from that perspective, this direction, okay, that's going to be the cross product vector. That's going to be the result of the cross product. Well, think about what that is, right? That's the z-axis. The z-axis pointing upward in particular, so what is that? That's k, okay? So if I took I and I cross it with j, I'm going to end up with k, okay? So now, let's take another one. Let's take my right hand, and now I've got, for example, I've got the j-axis here, and I'm going to cross it with the k-axis. J-axis crossed with the k-axis, where's my thumb pointing? My thumb is pointing back at you, okay? And what is that vector? That vector is the I vector, right? So I take j and I cross it with k, and I get that I vector. That's what's happening there, okay? Now let's take k. So I got k, okay? And I want to imagine k, and I'll dot it or cross it, not dot it, but cross it with I, k cross I. What do I get? I get j. K cross I is j. Now, so that actually is going to be kind of handy. And if you think about it, it makes sense. You've got an axis, and we talked about the cross product. If we take the cross product, we create a vector that's orthogonal to both vectors. Well, if I've got the x and y axis, the vector that's orthogonal to those two vectors is the z-axis, right? Okay, makes total sense. Now there's a little wrinkle in here, okay? And that is, for example, let's say, for example, that I take, instead, I'm now going to take the, I want to cross the j, I want j cross I. So I've got the y-axis, okay, I'm going to start with the y-axis, and I'm going to go now towards the I-axis, and now notice what's happened with my thumb here, okay? My thumb, right, is now pointing downward. So now it's that negative z-axis, or it's negative k. So if I take j cross I, right, I end up with negative k, okay? And the same thing is going to happen if, say, for example, I've got the k-axis, okay? And if I take the k-axis and I cross it with, if I take the k-axis and I cross it with the j-axis, right, now, notice my thumb is pointing back at me. That, in fact, is the negative I-axis, Okay? So those ones are going to become like, they're going to be our kind of like a hallmark. They're going to help us out quite a lot with doing calculation with the cross product. All right? And I'll enumerate those in just a second. But that's the geometry that's going on there. Okay? It's basically if I cross one of my coordinate axes with another coordinate axis, what I get is the other coordinate axis, and it'll either be pointing up or be pointing down, depending upon the order of the cross product. So let's look at these cross products of coordinate axes. Cross products of I, J, and K. So let's first talk, we've got I, okay, and we're going to cross it with J. I cross J, and so again, we're going to take our cross product, I, J, K, and I is 1, 0, 0, and J is 0, 1, 0. Okay? 1, 0, 0, and 0, 1, 0. So we'll start out with the ith value, and then we're going to take these four. So what you're going to notice is you're going to get 0 times 0 minus 1 times 0, I, plus, or rather minus, keep doing that. We'll take the j, and then the j is going to end up being 1 times 0 minus 0 times 0. So 1 times 0 minus 0 times 0, j, plus, and then now we've got 1 times 1 minus 0 times 0, k. And so what is that? That's just 1k, which is just equal to k, just like I said. Now we already talked about like what happens if we reverse that order, if we take j cross I instead of I cross j. So j cross I is going to equal then just negative k. That works out geometrically, and it's going to also work out, you can go in and do the calculation. Let's take j cross k. So j cross k is going to equal, I've got I, j, and k. And so now j is 0, 1, 0, and k is 0, 0, 1. Okay, so we end up with I times 1 minus 0 times 0. Okay, so we got 1 times 1 and 0 times 0. And you might notice that you're creating kind of a pattern. So we've got minus now, and so the j is going to be 0 times 1 minus 0 times 0. So 0 times 1 minus 0 times 0, okay, j, plus, and then k is going to be 0 times 0 minus 0 times 1. So that's 0 times 0 minus 0 times 1, and that k, so what does that give me? Well, the only one that's got anything that's not 0 is I, so that's going to end up equaling I. So j cross k ends up equaling I, right? The other. So negative j cross k, or excuse me, k cross j, then should equal negative I. And I'll leave the last one for you, and that is actually if I take I cross k, and you should think to yourself, oh, if I've got I cross k, right, go and do the calculation, I cross k should equal j, and then if I switch it around and make it k cross I, oh, excuse me, k cross I, pardon me, k cross I is going to equal j, and then I cross k ends up equaling negative j. Okay, so if we just take those standard unit vectors, I, j, and k, okay, what we get is we get some special vectors, right? Things that end up becoming really very, very handy, and we're going to utilize those quite a lot in just a moment. So a natural question that you might have is, what happens if I cross a vector with itself? Okay, well, let's actually just look at, let's say for example I have I cross I, and we'll take that as an example because it's really easy to kind of calculate. So I cross I is going to be, I've got I, I've got j, and I've got k. And then I've got 1, 0, 0, 0, 1, 0, or excuse me, 1, 0, 0, and 1, 0, 0 again. Now, one thing to notice here is that if I'm crossing here, right, that's going to end up being 0. Is there any way that I'm going to get like 1 times 1 to get my 1? I mean, if you really think about it, the answer is no. There's no way that I'm actually going to like get back 1 at all. Okay? It's just not going to happen. So what I'm going to get here, if I kind of look at this, I've got, first I'll start out with these zeros, because they've got I, so 0 times 0 minus 0 times 0, I, plus, or rather minus, 1 times 0 minus 0 times 0, j, excuse me, times 1 times 0, j, plus, and then 1 times 0 minus 1 times 0, k. Well, what do I get then? I get 0i minus 0j plus 0k. Uh-oh. Well, what is that? That's the zero vector. And if I actually think about it, if I have two vectors, I want to find another vector that is orthogonal to both vectors, orthogonal to I. Well, really only makes sense that it's going to be the zero vector. By the way, I want you to notice that this is actually the vector 0, 0, 0. It's not nothing. Okay, very important that this is not actually the nothing vector. All right, okay? We actually have values, and so our vector is really that thing, which is called the zero vector, which we oftentimes are going to write as 0. Okay? If we have two-dimensional space, this is the zero vector. Which actually brings us to a really important point, right? The first point is that, and you're going to see this in just a second, if I cross a vector with itself, I get back the zero vector. But another key point here is the result of the cross product is a vector. We have a second one, the result of the dot product is a scalar. So you notice that, right? We basically end up with something that's like kind of like a magnitude is a scalar, and then the result of scalar multiplication is another vector. So let's actually look at and prove what happens when we cross a vector with itself. So take v cross v. I got I got j, and I got k, my component vectors. So I got v1, v2, and v3. v1, v2, v3. And so when I cross them, what you'll see is you've got v2, v3, minus v3, v2, I, minus v1, v3, minus v3, v1, j, plus v1, v2, minus v2, v1, k. And if you go through and you do the math there, what you'll notice is that that's the same as that. So this is 0i minus, same thing. Those two are the same, so 0j plus, same again, 0k. Right? Which is the zero vector again. So the result of v cross v always equals the zero vector. All right, so we've got some pretty key results for working with cross products. Okay, on the one hand, that if you commute the cross product, that is, that if you switch its order, you end up with something that's the negative, right? So u cross v is equal to negative v cross u, right? We make a negative. Secondly, if we cross a vector with itself, what we get back is we get back the zero vector, right? And if we cross our standard unit vectors, we're going to get the missing standard unit vector back with accounting for direction. Now let's take a look at some properties of the cross product. So let's suppose that we have u, v, and w are vectors in space, and we're going to let c be a scalar. So two that we've already talked about is that u cross v is going to equal negative v cross u. And the second one is that v cross v is going to give us back the zero vector. Okay? So that's going to happen. Now a third one that should be pretty intuitive as well, basically is a zero property. And that's going to be that u, a vector u crossed with the zero vector, is going to equal the zero vector crossed with u. So it doesn't really matter what direction it is. And that's going to give me back the zero vector. So if I cross something with the zero vector, I just get back the zero vector. It's the only thing that we really can do. Okay? Then 4, I have something that's like a distributive property. Really important, it's a little bit different. So if I take u crossed with v plus w, then that actually ends up becoming the equivalent of u cross v plus u cross w, which is actually kind of cool. And if you want to actually see the proof for this, it's inside of our textbook. You can find it inside of any real textbook. It's not too hard. You can probably do it yourself too. Okay, nothing too difficult with that one. And that's distributive. And then 5, we've got, if we take a scalar and we multiply that by u cross v, it's actually going to either be, we can either multiply the scalar by the first vector and then take the cross product, or multiply the scalar by the second vector and take the cross product. What you want to notice is that it's not actually multiplying the scalar by both. It's only multiplying it by one. So it's not like distribution. Okay? So this multiplication by this constant is going to be either Cu cross V, or it could be U cross CV. It's another option. And that's also another one that actually is pretty easy to see. Okay? And you can look at your book in order to get the description of that, or to see the proof of that. And then our final one is going to be what's called a scalar triple. Okay, and we're going to talk a lot more about this one. And that's U dotted with V cross W equals U cross V dotted with W. And that's called the scalar triple product. And it's really important. It's not intuitive really at all if you kind of think about it. All right? Yeah, I mean, like, it doesn't look like it should work the way that it does, but it does. Notice that we can either cross V with W and then take the dot product with U, or we can cross U with V and take the dot product with W. Okay? Notice also it's a dot product, so both of these are going to be constants. So that's going to be a constant. That's going to be a constant because the result here is going to be the dotting of two vectors. So we're going to end up with a constant because we're taking the dot product of two vectors. And so those are actually our properties of utilizing the cross product. So now the next result that we're going to look at with regard to the cross product is actually very crucial. And it has to do with the magnitude of the cross product and its relationship to the magnitudes of its individual vectors. So let's suppose that we have u and v, they're vectors, and we'll let theta be the angle between them. Then the magnitude of the cross product, u cross v, is equal to the magnitude of u times the magnitude of v times sine theta, where theta is the angle between the two vectors. Okay? And so what we're going to do, I'm going to do just briefly, I'm going to actually go in and I'm going to prove this. Now, it's going to have a lot of indexing numbers, and they all come from the cross product, so try and follow along, all right? But don't be too upset if you're like, oh man, a lot of numbers, a lot of values, all right? What I'm really going to be doing is kind of like pointing out places where we've learned things before, where, you know, I'm going to use that important information that we got from before to kind of like prove this result. So let's start out with, we want to find the magnitude of u cross v, okay? We know that we know actually the components of each one. So the ith component for u cross v is going to be u2 v3 minus v2, or minus u2 minus u3 v2, okay, and we'll square that. So that's that component. Then the second component, it's a negative, so it's going to be plus, and it's going to be a negative, and it'll be then u1 v3 minus u3 v1, and we'll square that. So it actually ends up just being the same number. You can get rid of the negative if you'd like. Plus, and then we'll have u1 v2 minus v2 u1. And we'll take that one squared. Okay? And so if we go through and we actually expand these out, what do we get? We get u2 v3 squared minus 2 u2, or excuse me, minus, minus 2 u2 v3 u3 v2 plus u3 v2 squared plus u1 v3 squared plus, or minus, rather, minus 2 u1 u3 v1 v3 plus u3 v1 squared. So all I'm doing is I'm actually just distributing. I'm foiling. That's it. I'm just foiling. Plus u1 v2 squared minus 2 u1, that's u, this is u2 v1, u1 u2 v1 v2 plus u2 v1 squared. Okay, and so that's just an expansion out that we have there. And that's going to then equal, okay, if we go through here, it's going to end up equaling. So now what we're going to do is we're actually going to add in. So we've got, if you notice here, what we're going to have is we're going to have, we're going to get u1, we're going to add in a u1 v1, or u1 squared v1, u1 v1 squared, okay, the whole thing, plus, and then we'll have u2 v2 squared. All right, so that's actually, these things, they're not already originally in the original value, plus u3 v3 squared, okay? And we're also going to then subtract, or well, and then we'll add those to the squareds that we already have. We have a u2 v3 squared plus u3 v2 squared plus u1 v3 squared plus u3 v1 squared plus u1 v2 squared plus u2 v1 squared. And then we'll subtract, and we're going to subtract, and what we're going to subtract is we're going to have these three terms, because we added them, so we've also got to subtract them. So we're going to get negative u1 v1, or excuse me, minus u1 v1 squared. So that actually cancels these two. Great, because that's what I added in, so I don't want to add something that I didn't already have. Plus u2 v2 squared plus u3 v3 squared. And then I'm going to have this term, so plus 2 u2 v3 u3 v2. This term plus 2 u1 u3 v1 v3 plus this term 2 u1 u2 v1 v2, and all of that subtracted. And so what that then gives me, actually, what you can do, you have to think it through a little bit, but actually we end up with these two. They're actually a perfect square. It's a perfect square. It's actually a perfect square of trinomials. So it ends up being u1 squared plus u2 squared plus u3 squared times v1 squared plus v2 squared plus v3 squared. So honestly, am I going to expect you to do that? No. I just want you to kind of go, oh, okay, I kind of get it. All right, I can buy that. Minus, and then it'll be u1 v1 plus u2 v2 plus u3 v3, and it turns out it's that squared. So this minus thing, this whole thing becomes this, okay? And all of these additions here, they become this, okay? Why is that important? Well, it turns out this thing right here, those two, that's the magnitude squared of u and v. So we end up with, that's u squared, right? And then this one right here, that's v squared. And this thing right here, that's actually u dot v squared. So this is minus u dotted with v squared. Hey, cool. Okay? And we can actually do a substitution if you remember from our work with cross product or with our dot product. So this is now u squared v squared minus, and the dot product is v u cosine theta, and then all of that squared, which is then the magnitude of u squared magnitude of v squared minus the magnitude of u squared magnitude of v squared cosine squared theta. There you go. Now all I'm going to do is I'm going to factor out. I'm going to factor out u squared v squared. So u squared v squared factored out. And what I'm left with is 1 minus cosine squared theta, which you should recognize is Pythagorean identity. So it's going to be the magnitude of u squared, the magnitude of v squared, sine squared theta. So what we've shown is that if we take the cross product and we square it, okay, that's actually what that was, the squared, then what we get is we get this thing. So the magnitude of u cross v squared is going to equal the magnitude of u squared magnitude of v squared sine squared theta. Take the square root of both sides and we get the magnitude of u cross v is equal to the magnitude of u, the magnitude of v sine theta. Whew. Now this is going to come in really handy in just a little bit. But that's a pretty high-level proof, okay? It's going to take you a little bit. You might want to, go in and read it in your book. Take a look at this in the notes, okay? Note that this was squared. I know I said it, but I didn't write the little 2, okay? Or a little square it, actually, on the paper. So as you're going back in, that's what happened. It's just ending up being squared. And then that allows us at the end to take the square root of both sides, and we get our equality, which is going to be crucial. So let's use this property in order to do something cool. Let's say, for example, I want to find the magnitude of u cross v, and I've got u equals 0, 4, 0, and v is equal to 0, 0, negative 3. Okay? So what I'm going to do is I know that u cross v, the magnitude of u cross v, is going to equal the magnitude of u times the magnitude of v times the sine of theta. So I'm going to notice that basically, right, this is the y-axis. It's like along the y-axis. This is also along the z-axis. Okay? And so consequently, right, they have an angle of 90 degrees between the two of them, or pi over 2. Yes? Pi over 2, that's going to be the angle between the two. And their magnitudes are really easy, because the magnitude of u is just going to be 4, and the magnitude of v is going to be 3. Okay? Given the fact that, you've got one vector, it's along the y-axis, and it's got a value of, it's 4 along the y-axis, so its length is 4. And then we've got v, and its length is negative 3 along the z, so it's got a length of 3, right? If I kind of drew it out, you could kind of see it. So we got boop, 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 boop. This one's going down this way, okay? So 4, right? 1, 2, 3, 4. How long is that? That's 4, right? That's going to end up being u. And then z, 1, 2, 3, is negative 3. Okay, so its magnitude is 3. Okay, there's your z. And because they're just different axes, I know it doesn't look like this because of the paper, the theta, okay, is going to equal pi over 2. All right, so magnitude of u equals 4, magnitude of v equals 3. Consequently, the magnitude of u cross v, right, is going to end up equaling 4 times 3 times sine of pi over 2. So that equals 12. I know it took a little longer for me to explain it versus just do the cross product to find its magnitude. But had you really thought it through and understood what was going on, that literally takes seconds versus finding the cross product and then taking its magnitude, right? You can actually see that we're going to do stuff like this throughout the entire class where it's like, okay, the math has made it easier or it's made it more efficient for me to do something different, right? So like this theorem makes it more efficient for me to find the magnitude of the cross product. All right, so now let's do something that actually is really important, really, really valuable, and that we're going to utilize a lot inside of our next chapter. And that is we're going to use the cross product. So let's say, for example, we want to find a vector that is orthogonal to 2 other vectors, right? This is something that we're going to do a lot of. So we want to find a unit vector that is orthogonal to, we've got the vector A, which is 4, 0, 3, and B, which is 1, 1, 4. Okay? Well, we know that actually the cross product is going to end up giving me, the cross product is giving me a vector that's orthogonal, right? So I'll go out and I'll find my cross product. So I want to find A cross B. Okay? And that'll equal, and I've got I, J, and K. So I'm going to utilize this method, which we actually is going to be called the determinant method. So it's 4, 0, 3, and 1, 1, 4. And so that'll equal right? 0 times 4 minus 1 times 3, I, minus 4 times 4 minus 1 times 3, j, plus, okay, 4 times 1 minus 0 times 1k. And so this ends up equaling negative 3i minus 13j plus 4k. All right, so that's the vector A cross B. Now, we know that that's going to be orthogonal to both A and B by the definition of our cross product. That's what the cross product is. It generates orthogonal vectors. Now we need to make it unit, okay? So a unit vector is generated by dividing the vector by its magnitude. So we're going to take this one, we're going to take A cross B, and we're going to divide it by the magnitude of A cross B. Now you might think to yourself, hey, why don't I use that thing that I did before? Okay, the problem is that, well, finding that theta, it might actually take you longer than it would take to just go out and find the magnitude of the cross product, because you already have the cross product. So we're going to have negative 3i minus 13j plus 4k, and we'll divide it through by the square root, okay, of negative 3 squared plus negative 13 squared plus 4 squared. Okay, so this is 169 plus 9. And so that ends up equaling negative 3i minus 13j plus 4k divided by the square root of 194. And what we can do then is we can just make that negative 3 over square root 194i minus 13 over square root of 194j plus 4 over the square root of 194k. And that is our unit vector that is orthogonal to both of those vectors. That's going to be actually a very key thing that we're going to be doing later on inside of the class. Okay? So let's try it again. Let's say we have A equals 5, 2, 1. And then we'll have B equal to 0, negative 1, 4. So what I'm going to do first is I'm going to find A cross B. And that's going to be, I've got my I, I've got my J, I've got my K. I've got 5, 2, negative 1, 0, negative 1, 4. And so this is going to be, okay, 2 times 4, 8, minus 1, so 7i, plus, and then this will be 20 minus 0, so actually minus 20j, plus, okay, and then this will be now negative 5 minus 0, so that's negative 5k. And that is A cross B. Now, we find the magnitude of A cross B. And that's going to equal the square root of 7 squared plus negative 20 squared plus negative 5 squared. All right, and that equals just the square root of 474. So my unit vector in that direction is going to be 7 divided by the square root of 474i minus 20 divided by the square root of 474j plus or minus 5 divided by the square root of 474k. And there we go. And there is the vector that is orthogonal to both and is in fact unit as well. Like I said, actually a really key thing. Something to notice about this is had we switched it, made it B cross A, the vector would still be orthogonal to the other two. It would still be unit. It actually would have the same exact magnitude, but it would actually be pointed in the opposite direction. Okay? Still orthogonal, just pointed in the opposite direction. All right, now what we're going to get to is actually a really important result. And it took a lot of work to kind of get here, but it's been worth it. I would say it's worth it. It actually turns into something that ends up being very handy, especially as you do more linear algebra and you work more with vectors. And that has to do with the relationship between this cross product, or what we'll get into called the determinant, and the area of a parallelogram. So the area of a parallelogram is given by its base times its height. So let's imagine that I've got two vectors, v and u. Okay? So imagine v and u. So here's v, here's u. And if we add the two of them together, we get a parallelogram, right? Okay? Remember, that's how we do vector addition. We end up with a parallelogram right here. Okay? And so we want to calculate its area. So the magnitude of u is the base. The base is going to equal the magnitude of u. That should be pretty obvious, right? Because u is the vector and its magnitude is its length. So there it is. This thing here, that length right there, if we kind of construct a right angle between the corner and the bottom of the parallelogram, that's going to end up being the height. And the height of the parallelogram is, oh, look at that, we've seen it again, it's v sine theta. V sine theta, because v is this vector here, right? That's like kind of the radius of the circle. And so the length of the highest side is going to be v sine theta. So consequently, our height is v sine theta. So the area A equals u times v sine theta. Oh, snap. What is that also equal to? If you remember earlier, that's actually equal to the magnitude of its cross product, or the magnitude of the cross product. And that's it. That's actually how we find the area of a parallelogram. So like, let's say, for example, I want to find the area of the parallelogram formed by, okay, 0, 1, negative 3, and 2, 4, negative 1. Well, I've actually just proven this. It's nothing too terrible. So I just got to go in, I got to find my cross product. So I find my cross product. Okay, I got I got j, I got k. I got 0, 1, negative 3, 2, 4, negative 1. And so the cross product of those two, okay, is going to end up being, we'll have negative 1 plus 12, I, minus 0 minus negative 6j plus 0 minus 2k. 0 minus 2k. And so this ends up equaling 11i plus, minus 6j minus 2k. And that is the cross product of those two vectors. Now I've got to do is I've got to go find the magnitude. So the magnitude of these two, we'll call them u and v, is equal to the square root of 11 squared plus negative 6 squared plus negative 2 squared, okay, which ends up equaling the square root of 121 plus 36 plus 4, which equals root 151. And that is the area of the parallelogram formed by those two vectors. You don't even need to draw it. Nice. Okay, going to actually come in really handy, something that you want to be able to do. Another application of this fact might actually be to find the area of a triangle formed by I, j, and k. So let's say, for example, we've got I, j, and k. We know I equals 1, 0, 0. J equals 0, 1, 0. And k equals 0, 0, 1. Okay? And so, or triangle formed by their terminal points. Let's say there's their terminal points for each one. And we'll just think about that. That's a triangle that kind of looks like this, if you imagine it in 3 dimensions. All right, we got 0, 0, 1 here. We've got 0, 1, 0 here. And we got 0, 0, 1, 0, 0 here. And those are those points. Okay? And we want to imagine, okay, so I've got this vector here and this vector here. Okay? And you'll notice that this triangle is actually, it's just half of a parallelogram. It's half of a parallelogram formed by, okay, essentially the vectors that connect, right, that connect these these different points in space. So what I'm going to do is I'm going to figure out, I'm going to call this PQ, okay, that vector PQ, and I'm going to call this one here, I'm going to call it PS. So it's vector PQ and vector PS, okay? And so PQ, right, is just going to end up equaling the vector, it'll be 1 minus 0, so it'll be 1, 0, negative 1. Okay, because you're just going to take 1 minus 0, 0 minus 0, 0 minus negative 0 minus 1. And then PS is going to equal 1, negative 1, 0. And that's the other vector. Now what I'm going to do is I'm going to find the area of the parallelogram, and then I'm going to divide it by 2. Okay, so the area of the parallelogram, remember, is going to equal the cross product of PQ crossed with PS. So that's going to end up being the area of the parallelogram, and that'll equal, I got I, you got J, you got K, okay, 1, 0, negative 1, 1, negative 1, 0. And so this ends up equaling 1 I minus, and then with our J, we've got 0 minus negative 1, so that's minus 1J plus, and then our kth term is going to be negative 1, so it's going to be negative 1K. Cool. So 1I minus 1J minus 1K, okay? And that's our resulting, the resulting vector, that's our cross product. Now we just have to find the magnitude. Excuse me, that's the cross product's this. So now the magnitude of PQ cross PS is going to equal, okay, and actually, if you kind of think about it, the two vectors are separated by they've got an angle of 60 degrees between the two of them because it's equilateral, but it's neither here nor there. So this is just going to be the square root of 1 squared plus negative 1 squared plus negative 1 squared, which equals the square root of 3. All right? And so consequently, that is the area of the parallelogram. But we only want to know the area of the triangle, so what do we need? We need to divide it by 2. The area of the triangle equals root 3 divided by 2, because it's half of the parallelogram. Right? Half of the parallelogram. And that's another application of finding the area of the parallelograms and our cross product.